So first of all, let's start with discussing confidence intervals and hypothesis testing for single group proportions. So just as a way of a quick review, if you'll remember that we have a way of approximating the binomial distribution using the normal distribution. And that's because the binomial distribution becomes more and more bell-shaped and normal-ish, if you will, as the sample size n increases. And as the expected proportion of successes on any given trial, which are denoted by pi, as that expected success approaches 0.5. So a perfect example is flip of a coin. You have a 50% chance of getting heads or tails. So by the central limit theorem, the sampling distribution of means for large samples resembles the normal distribution. So when it comes to proportions, even if the proportion is not very close to 0 or 1, but if n is large, by which we mean 30 or more, the binomial distribution still becomes close to a normal distribution. And so what all this means is that you can use z-scores and the standard normal table to compute binomial probabilities. And so that's what we're going to be doing. So again, by way of review, the equation for a z-score for a standardized binomial variable, there are two different equations. In this equation, we have the z is equal to, in the numerator, the number of successes in your sample, x minus the number of trials in the sample multiplied by the probability of success on any given trial. And then in the denominator, we have the square root of n multiplied by pi multiplied by 1 minus pi. Another way of calculating z, which we'll be using more often in this lecture, so rather than working with a number of x successes in n trials, we're dealing with the fraction of successes in n trials. So if x is your number of successes, you just divide it by the number of trials. Say you flipped a coin 10 times, that would be your number of trials. You got 3 heads. That would be x. Your f, your fraction of successes in that case, would be 0.30. So when we're dealing with a fraction, our z statistic's a little different. It's f minus pi divided by the square root of pi multiplied by 1 minus pi, and then all of that divided by n, which is the sample size. And so we'll be using that equation in our example. So I also, a few lectures ago, talked about equations for the mean and variance and standard deviation. So you can see them there for the binomial fraction of success. The mean, the expected value of f, is pi. The variance of f is pi multiplied by 1 minus pi, and that's divided by n. And then for the standard deviation of f, you just take the square root of that. Okay, so first let's talk about confidence intervals on binomial proportions. So as long as we have a sample size of 30 or greater, then we can assume the binomial sample distribution is approximately normally distributed, and so we can use the z distribution for these intervals. And so you can see there the formula. Remember, the confidence intervals, typically they're 95%, but they have a left side and a right side to the interval. And so this formula should look very familiar because it's similar to what we used for the means, confidence intervals around the means. Except in this case, we're taking the fraction of success for the left side minus whatever value of z we have with a given alpha value, and so that would be the same as like what we did for the means. So if alpha were equal to 0.05, z alpha 2 is 1.96. So it would be f minus 1.96 multiplied by the square root of f, which again is the fraction of successes, multiplied by 1 minus f over n. And so for the right side of that formula, everything is the same except for, instead of subtracting z multiplied by that square root from f, we're adding it to f. And so then we get the right side of the formula. So in terms of a step-by-step recipe, again, I've put some of these step-by-step recipes that I'm going to go over in this module. I've also copied these into a document and that I'm going to upload onto Blackboard for you to use. So the first step is you want to compute F, your fraction of successes. Then you want to choose your desired alpha value. Alpha 0.05 implies a 95% confidence interval. Then your next step is to find the z-score in the table corresponding to z at that alpha level divided by 2. Remember, because we want to find the z-score for the left and right tails of the distribution. So we divide it by 2. So if alpha were equal to 0.05, we're looking for the value at 0.025. So to find the z-score, remember, in the table, we subtract 0.025 from 0.5, and that gives us 0.475, and then we look up the z-score, corresponding z-score, and that is 1.96, plus or minus 1.96, and then we plug that in to compute the left and right side of the confidence intervals. So here's an example. Let's say we have 100 decedents from a drug overdose, and 65 of those deaths were due to non-illicit drugs. The question is, what is the 95% confidence interval for a proportion of drug overdose deaths due to non-illicit drugs? So our fraction of success, in this case success is dying due to non-illicit drugs, is 65 divided by 100, so that's 0.065. So we plug that into our formula. On the left side you see we have 0.65. We're interested in 95% confidence interval, so our z statistic is 1.96. So we have 0.65 minus 1.96, and that's multiplied by the square root of 0.65 times 1 minus 0.65 divided by 100, and our result is 0.56. When we plug that exact same formula into the right side, except this time we're adding z multiplied by our square root product there, we get 0.74. And so now we can say we're 95% confident that the true population proportion of drug overdose deaths due to non-illicit drugs is somewhere between 0.56 and 0.74. Okay, so what about hypothesis testing for a single group proportion? Now here our objective is to test whether the sample proportion, so the proportion that we find in our sample, is outside the range of what was previously believed to be the overall population proportion. Again, our assumption is that when our sample size is greater than or equal to 30, we can assume the binomial sample distribution is approximately normal, and we can use the z distribution. And so in terms of our hypotheses, here remember we're hypothesizing about pi, which is equal to the proportion of successes in the population. And so we can have a one-tailed left-sided hypothesis, which would be our alternate hypothesis would be that pi is less than some value that was previously assumed in the population. So the proportion of successes is less than what we previously assumed it to be some value. The null is that it's greater than or equal to that. A one-tailed right-sided hypothesis would be that pi is greater than some previously assumed value in the population, and then the null would be the reverse of that, which is that pi is less than or equal to that previously assumed value in the population. And then lastly, we can have a two-tailed hypothesis. So here the alternate hypothesis is that pi, the proportion of success in the population, is not equal to some previously assumed value in the population, maybe the prior value that everyone thought it was. And the null hypothesis is simply that pi would be equal to that value. So we want to use the z statistic, and again here, so I'm showing you the formula for the z statistic, whether we're dealing with n and x. X is remember, is the number of successes in the sample, or f, which is the fraction of successes in the sample. You can see the z statistic in either case. We'll be using the fraction of successes, so z is equal to, in the numerator, you have f minus the population probability of success. So this is the prior or assumed probability of success on any given trial, whereas F is the observed frequency of success in our sample. And then we divide that by, in the denominator, again, that pi naught, which is the population prior probability, multiplied by 1 minus pi naught, and then divided by n, which is your number of trials in the sample. Often we set pi naught equal to 0.5, which assumes random chance, right? If you have one of two possible outcomes, then without any prior knowledge, due to random chance, your chance of getting one outcome is 0.5. And so we're often trying to set that as the null hypothesis and then disproving that null hypothesis that our sample results are due to random chance. So here's a recipe for hypothesis testing for a single group proportion. And again, I put this in the document that I'm posting to Blackboard. So first of all, you set up your null hypothesis, which is that pi is equal to pi naught. And if we're doing a two-tailed hypothesis, and your alternate hypothesis, that it's not equal to that null value. Then you choose your desired alpha value, for instance, alpha equal to 0.05, and you want to compute the frequency of successes in your sample. So this would be x, your number of successes, divided by n, your number of trials. Fourthly, you want to identify the critical value of the z-score for your to reject the null hypothesis. So you look up the two-sided or two-sided z-score, remember, depending on whether your hypothesis test is two or one-tailed. So if it's alpha is 0.05 and it's two-tailed, then you find z for alpha at 0.025, and that corresponding z-score would be plus or minus 1.96. If alpha were equal to 0.05 and you're doing a one-tailed test, then you're finding z for alpha at 0.05, and that z-score is plus or minus 1.64. Also note that you want to make the critical value of the z-score negative if your alternate hypothesis is left-sided, meaning that the proportion you're finding in the population is less than the previously assumed population proportion. Fifthly, you want to compute the z-statistic using the formula I showed you on the prior page. If your computed z-statistic is greater than the critical value of z that you've looked up in the table, such as, say, it's 1.96, then you reject the null hypothesis. But note that if your alternate hypothesis is left-sided, then you reject the null hypothesis if your z-statistic is less than the critical value of z, because it would be negative in that case. So let's take an example. So we have a sample of 100 people, and they're offered a gift certificate or cash. The number of people who choose the gift certificate instead of cash is 30. Our question is there any difference between the probability of choosing a gift certificate or cash? So we set our null hypothesis up to be 0.5 because we want to disprove the null that it's just a random chance of accepting the gift certificate or accepting cash. We want to say that there is some difference and that it's not just a flip of the coin. So then our alternate hypothesis is that pi is not equal to 0.5 or random chance. F, the frequency of success, is 30, the number of people who chose the gift certificate, divided by 100, our sample, number of trials, so it's equal to 0.30. Our alpha value, we're going to set it at 0.05, and so that makes our critical value for the z-statistic to be, actually that should say 1.64, not 1.96, because this is no, that is correct, 1.96. This is a two-tailed test, so it would be 1.96. Okay, so then we compute the z-statistic. That would be equal to 0.3, which is our value of f, minus 0.5, which is our null hypothesis for the proportion, divided by the square root of 0.5 multiplied by 1 minus 0.5 over 100. And so our resulting z-statistic is -4. And so that z-statistic of -4 is less than a critical value of -1.96. And so we reject the null hypothesis, and we conclude that people are less likely to choose a gift certificate than cash.